This talk is Going Beyond Coverage-Guided Fuzzing with Structured Fuzzing by Jonathan Metzman. But first, we have a few notes. Please stop by the Business Hall located in Mandalay Bay, Oceanside and Shoreline ballrooms on level 2 during the day, and for the welcome reception at 5:30 this evening. The Black Hat Arsenal is in the Business Hall on level 2. And join us for the Pony Awards in Lagoon JKL at 6:30. Please remember to silence your phones. And without further ado, Jonathan Metzman.
Hi, everyone. Thanks for coming to my talk. As I was introduced, I'm Jonathan Metzman, and I'm here to talk about how you can get more bugs out of coverage-guided fuzzing by adding structure awareness to your fuzzers. I first got into fuzzing while I was in college through AFL. I started using AFL to find bugs in my school projects, and later I moved on to finding bugs in real software like SQLite with AFL. And I was really amazed by how well AFL worked because, I didn't really know much about how AFL worked at the time, and I didn't know much about the software I was finding bugs in with AFL, but it still worked so well. And I thought, what could be better than this tool that gives us bugs for free? So I think the answer to that has got to be structured fuzzing, otherwise I wouldn't be giving this talk. But unfortunately, structured fuzzing doesn't actually give you bugs for free. It forces you to think about the format that you're fuzzing, but because of that thought process and the effort you put into it, you'll end up finding more bugs. So let's fast forward a few years to when I started working at Google. I wrote a structured fuzzer for Skia, which is a graphics library used in Chrome. And you could see part of the header file of that fuzzer on the screen. And so as you could probably guess, it took quite a bit of effort to write that fuzzer. But I think the effort paid off in the end because the fuzzer found around 10 vulnerabilities in Skia that weren't found with unstructured fuzzers like AFL. So today I want to teach you more about this technique, structured fuzzing, and convince you why it's sometimes worth it to pay more when you could pay less. First, a little bit about myself. I work at Google mainly on fuzzing Chrome, but we also develop fuzzer tools that are used by other open source projects, and one of these is called OSS Fuzz, which thank you, Dino, for shouting us out during the keynote today. And one of the unofficial roles I've taken on in Chrome security is getting people to write structured fuzzers for Chrome. They've been such a big win for us there, and I'm hoping today I could do the same for you, and that they'll be a big win for you all as well. So let's define what I mean by structured fuzzing and see how it evolved. The first generation of fuzzers were completely black box. They knew nothing about the target that they were fuzzing, and they were also actually structure unaware, which means that they knew nothing about the format that they were supposed to be mutating or generating. So they were pretty rudimentary in that they were similar to piping bytes from dev random to like a Unix utility, just completely unaware. And now the next generation of fuzzers improved on the effectiveness of the first generation by being structure aware. They were still black box, but this was probably based on the realization that if you're fuzzing something like an HTML renderer, you're more likely to find bugs if you give it inputs that look something like HTML rather than just nonsense from dev random. Now, I think the current generation of fuzzers that most people are using are coverage-guided and unstructured. And this is the technique that AFL pioneered and has sort of sparked this fuzzing revolution that we're in currently. And the reason why AFL has had such a large effect in this technique as well is because unstructured fuzzing allows people to use it without actually understanding much about the format that they're actually fuzzing. But because it's coverage guided, the fuzzer generates progressively more interesting inputs, and that's why it's actually fairly good at finding bugs. Now, coverage guided fuzzing is such a big advance in fuzzing that I'm going to just assume we're talking about coverage guided fuzzing throughout the rest of the talk. And so I'm just going to refer to this as unstructured fuzzing. Now, I think the next generation of fuzzers will build off of these advances in coverage guided fuzzing, but they'll also be structure aware. And this is what I call structured fuzzing. And by being structured aware, I mean things like They won't do the sort of general purpose mutations that AFL does on inputs. They'll do format specific ones, like they'll delete expressions from JavaScript programs. They won't just flip bits. So why use structured fuzzing? At the end of the day, I think it's only worth using a new fuzzing technique if it helps you find more bugs. And that's exactly what structured fuzzing can do for you. So let me first demonstrate that structured fuzzing can help you find more bugs and explain why it'll help you find more bugs. And to do this, I want to start by sharing a story about how structured fuzzing found bugs in SQLite that weren't found with unstructured fuzzing. Now, I mentioned fuzzing SQLite in the earlier slides, or at least one of the first projects I would fuzz with AFL was SQLite. And I'd guess that probably SQLite might be one of the most well-fuzzed projects in the world. One of the groups that fuzzes SQLite is actually my team at Google. We fuzz SQLite through OSS Fuzz, and we've been doing it for years through libFuzzer and AFL. And I'd say that over the years, we've probably thrown tens of billions of test cases at SQLite that were created by AFL and libFuzzer. So you would think that with all these attempts and all this time, AFL and libFuzzer would have found most of the bugs in SQLite. But obviously, that's not true. And we actually have one of my coworkers actually last fall, Matthew Denton, wrote a structured fuzzer for SQLite. And this fuzzer would generate SQL statements to be executed by SQLite. And it immediately started finding vulnerabilities that weren't found by AFL and libFuzzer, including this heap overflow that you see on the screen. Now, that's just an anecdote, but we actually have data to support the use of structured fuzzing as well. In Chrome, probably around 50 vulnerabilities have been found using structured fuzzing in about the past 2 years. And some of these were cases like the previous one, where there was a unstructured fuzzer, and then the structured fuzzer sort of beat the unstructured fuzzer in finding bugs. But actually, there are other cases where structured fuzzing allowed a researcher to fuzz code that they couldn't fuzz with unstructured fuzzing. And I'll explain more about how that works later on. And although I'll only be discussing structured fuzzing in the context of like userland code and libFuzzer today, it's worth noting that outside of this context, there's a lot of data to support the use of structured fuzzing as well. I think the most notable of these is syscaller, which for those of you who haven't heard of it, is a structured fuzzing framework for the Linux kernel that has found, I think, over 1,000 vulnerabilities in just the past couple years. So why does structured fuzzing help you find more bugs? There are many reasons, but I think they all really boil down to the fact that structured fuzzing gives you, the researcher, more power to fuzz what you want. It lets you fuzz where you think the bugs are going to be. Let's see how this compares to unstructured fuzzing at a high level. So if we're fuzzing something like V8, which is Chrome's JavaScript engine, there's a range of possible places where bugs can occur. On one end of the spectrum, you've got bugs like parser bugs. And then on the other end, you have things like JIT miscompiles, where you actually have to run JavaScript code to trigger those bugs. Now, what an unstructured fuzzer like AFL would do if you were using it to fuzz V8 is it would take JavaScript programs and it would pick random bytes in those programs and change them to arbitrary values. So if we have like an else keyword in our program, AFL might do something like add a 0 into the middle of our else keyword. And this is going to fail parsing, right? L0SE is not valid JavaScript code anymore. And this is sort of the problem with using unstructured fuzzing sometimes. So many of the test cases are going to fail parsing that while you might have an easy time finding these sort of parser bugs, you're going to have a much harder time finding these bugs that exist higher up the stack, at a higher level of abstraction. And so to focus on finding these bugs that live at this higher level of abstraction, we can, with structured fuzzing, we can constrain our input so that all of our inputs to the target obey certain constraints. So with the structured fuzzer, we can make it so that every test case we create is syntactically valid JavaScript. And so we can be sure that all of these end up getting executed. And this is basically what I mean by sort of fuzzing where you think bugs are. You're basically focusing the fuzzer's efforts on a certain subspace of the range of possible inputs that you think is most likely to trigger bugs. And it's also worth noting that in V8 in particular, and I think it's true for most programs, most bugs actually tend to live at these higher levels of abstraction and not just at the parsing level. So by doing this, we are really finding more bugs. Another way that controlling your input space with structured fuzzing can help with fuzzing efficiency is you can avoid fuzzing certain code that actually makes it harder to find bugs. And so recently I was writing a structured fuzzer that produced JavaScript code, and one of the problems this fuzzer had was it immediately started producing infinite loops. And we don't want to execute infinite loops when we're fuzzing a JavaScript engine like V8 because it's a huge waste of time. You know, we'll never be able to reach code that comes after the infinite loop, and instead we'll just keep trying the same thing over and over again and expecting to find a bug. So the simple solution with structured fuzzing is, again, constraining the input space. So now, instead of just generating syntactically valid JavaScript, I'm only going to generate syntactically valid JavaScript where every loop is bounded. And this obviously solves the infinite loop problem that we have. And you can apply this to other sorts of issues you might face when fuzzing. So you could do the same to ensure that, you know, your JavaScript code doesn't throw any uncaught exceptions, for example. Now, I think the real power with structured fuzzing is not in just avoiding fuzzing certain things, but it's in making the fuzzer cover code that you want to be tested and you want to find bugs in. And a good example of this was a fuzzer I was recently writing for PDFium, which is Chrome's PDF reader. Now, the way I wrote this fuzzer was I would run the fuzzer for a little bit, then generate a coverage report using Klang's coverage tools, and see what code wasn't being covered. And so, as you can see on the slide, there's a coverage report that shows that the PDFium's barcode feature isn't being covered at all. And there's a simple reason for this. It's because I had no idea that PDFs actually support barcodes, that that's like a feature that they have. But apparently, it's actually a thing. So the solution here was just to basically expand the input space to get the fuzzer to produce PDFs that contain barcodes. And then I ran another coverage report afterwards and just confirm that I'm indeed covering the code I wanted to cover, the barcode feature. Now, this workflow is something you only really get with structured fuzzing. With an unstructured fuzzer, you could sort of get it by, you know, giving seed inputs and hoping that it can derive similar inputs from there. But it's not like a tight feedback loop like you have here. And, you know, here with structured fuzzing, you're almost becoming like part of the fuzzer, where you see code that isn't being covered, and you know, make a decision whether you think it's worth covering that code, and then you make the fuzzer cover that code. And that's a point I want to emphasize here, that, you know, we're making a trade-off with structured fuzzing where we're trading some of our time and effort in order to find more bugs. And, you know, you'll just have to decide if you think it's worth covering like one feature or another feature, or covering a feature more thoroughly, or maybe you can get bugs more cheaply by teaching the fuzzer about another feature. Like you'll notice, I'm not covering the barcode feature fully in the second coverage report, and that's because I decided, hey, you know, I could probably get more bugs by teaching the fuzzer about a new feature. You know, I've already gotten bugs out of this barcode thing I did. The last way I'm going to cover that structured fuzzing can help you fuzz where you think bugs are is structured fuzzing can actually make it easier to fuzz code that doesn't just accept an array of bytes. So a good example of this that I want to use to illustrate this point is a fuzzer written by a coworker of mine, Ned Williamson. This fuzzer was for app cache, which is a Chrome feature. App cache had a number of APIs that the fuzzer was trying to find bugs in. And you'll notice that none of these APIs just accept a blob of bytes like unstructured fuzzers produce. And so there's also no place in Chrome where you could just shove in a blob of bytes and get these functions exercised. So what the fuzzer did was it structured each of its inputs so that each input represented a function call to make and the arguments to pass to those functions. Now, obviously, this input can't be directly used in fuzzing. There's nothing in Chrome that understands what this means. So the fuzzer also just had to interpret these inputs. So it says, if the input's telling me to call doRequest, I'm going to call doRequest and pass in the specified arguments. So to summarize why you should use structured fuzzing, You should use it because it'll help you find more bugs. And it can help you find more bugs because it gives you, the researcher, more power into fuzzing what you want, and also because it allows you to fuzz more things. In particular, it allows you to fuzz code that doesn't accept an array of bytes. Now that I'm done selling structured fuzzing to you all, I want to give you very practical advice on how you can write a structured fuzzer. And I'll cover 3 techniques that you can use for writing a structured fuzzer with libFuzzer. And libFuzzer, for those of you who don't know, is a coverage-guided fuzzer, much like AFL. It's probably the main fuzzer that we use in Chrome and OSS Fuzz. So the first way you can write a structured fuzzer with libFuzzer is by defining a libFuzzer custom mutator. And these work pretty much as you might expect. You simply define this function, and libFuzzer, when mutating test cases, will call this function to mutate test cases rather than its default mutator. So if we're fuzzing JavaScript, instead of using the default mutator to do stupid things like bit flipping, we'll actually, libFuzzer will call your custom mutator that can do things like, parse the JavaScript, build an AST, and then do sort of like intelligent mutations. It's a lot of work, but this technique is pretty powerful. There's an easier way though, and that's where libProtobuf Mutator comes in. libProtobuf Mutator will actually handle mutation for you, and you only have to do work around there. So let me explain what I mean here. So libProtobuf Mutator is a custom mutator for Protobuf, just like the custom mutators we just discussed. And Protobuf is a data format like JSON, but with types. And so what you can do, the insight here is you can use Protobuf to define like a spec or schema for the inputs you want libFuzzer to mutate. So if you see on the slides, we have an add expression defined in Protobuf. And in this simple case, we'll have 2 operands that are both integers. But Protobuf is rich enough that you can make each operand, an int or a float, or an int float, or another expression even, It gives you the tools that you'd probably want in this case. So libProtobuf Mutator will then create a test case based on this spec for you. And as we see here, we've got 2 operands, 10 and 9. And that's basically exactly what we intended. And so obviously, like we saw before, you can't feed this to anything unless it accepts Protobuf, right? It's not useful for fuzzing something like V8. So what we do is we have our interpreter for this, and our interpreter here will just convert from this intermediate format into the target format JavaScript. We'll take both operands, convert them to strings, and add a plus sign in between them. libProtobuf Mutator is extremely effective, and actually all of the fuzzers that I've covered today have used this technique. This includes everything from like the Skia fuzzer to the app cache fuzzer, which the app cache fuzzer actually was used in a used in an exploit that had a sandbox escape and everything. So completely owning Chrome with the vulnerability found by the app cache fuzzer. And actually, the Protobuf Mutator was again used by my coworker Ned to find the vulnerability in the iOS kernel that was used in the iOS, I think 12.2 jailbreak. So you can use it to find some pretty nice bugs, and it's sort of the technique I'd recommend in most cases for writing a structured fuzzer. The last option you have is one that's like a pretty exciting area, more for future work, but I don't have fantastic results from it so far, so I'll just sort of explain it and maybe give some tips on how you might be able to do it. Now, imagine you have a black box fuzzer, basically something like a Python script that can mutate HTML files that you then feed to Chrome and try and get crashes. You could convert this into a libFuzzer custom mutator to add the power of coverage-guided fuzzing to this black box fuzzer that you have. And so some of the challenges that you might encounter when doing this that you might have to overcome are, if you imagine how this fuzzer works, you'll have a corpus of test cases, and your fuzzer will pick one at random, mutate it, and that gets fed to your target. Now, if it were a custom mutator, what would happen is there's pretty much the same, but there's a last step at the end where a test case will be added back to the corpus. And this could present a problem for some fuzzers because they can't actually mutate their own output sometimes. They're not used to be running in a kind of loop. I was recently converting a font mutator into a libFuzzer custom mutator. And the problem there was, this font mutator would parse what expected to be semi-valid fonts and mutate them, and that I would then feed to the target. Well, once it was mutated, it sometimes wouldn't be able to parse those mutated outputs again. So in that case, you could just sort of fall back to the libFuzzer's default mutator, or even maybe improve your mutator. The other problem you might have to overcome is sometimes these tools aren't written to be fast enough to run in this coverage-guided fuzzing loop. Coverage-guided fuzzing works best when it's quick, and you might need to improve the speed there. And the final thing you might need to improve is, or work on, is the fact that many of these test cases, these mutators, are written in languages other than C++. And to call it from a custom mutator, you need to use whatever language the fuzzer's written in. It probably has some interface, like maybe JNI, for calling that code from C++. So to summarize how you can write a libFuzzer how you can write a structured fuzzer using libFuzzer, your first option is to use a libFuzzer custom mutator. Your second option, and it's the one I recommend in most cases, is to use libProtobuf Mutator. And the third thing you can do, which is pretty exciting, is taking an existing black box fuzzer you have and converting it to a libFuzzer custom mutator to get the power of coverage-guided fuzzing added to your fuzzer. So to summarize what we went over in this talk, you should use structured fuzzing because it'll help you find more bugs. More bugs is really the bottom line here. And to write a structured fuzzer with libFuzzer, you can use either libFuzzer's custom mutator feature or libProtobuf Mutator. I have some links at the end of the slides if anyone wants to check the slides afterwards and do further reading. And I'll take questions now if anyone has them.
Hi, I have a question.
Can you go up to the microphone and ask there? Thank you.
Hi, so you talk about writing new fuzzers from scratch.
Yeah.
However, last year there was a fuzzer released which kind of does all this. Are you aware of the AFL Smart?
Yeah, I have heard of AFL Smart. I skimmed the paper, but it seemed to me like it was pretty much a similar idea to libProtobuf Mutator, where you take, you sort of write like peach pits, and yeah, it's just a similar idea, I think, to libProtobuf Mutator. You're like defining, you're defining a schema for what you want mutated.
Yeah, you basically define the pitch files where you have the grammar, and you also have all of the advantage of the AFL with the speed and efficiency, and you can make it structure aware by defining the grammar by yourself.
Yeah.
So yeah, you pay by investing time in defining grammar, but it has really good results in real life. Yeah,
yeah. I mean, I'm familiar with I'm a little bit familiar with the work, and yeah, they, I know the people that did it, they produce pretty good work on AFL, and yeah, I was pretty impressed with the results, and I think it's pretty comparable to libProtobuf Mutator. So yeah.
Yeah, because I was curious if you're using it.
We're not using it, but I'm currently exploring ways to do this better, and so that's definitely one of the things I'm going to be looking at. Yeah, because I mean, Protobuf isn't like a, it wasn't designed for making fuzzer grammars, right? And so, maybe something like Peach's pits would be better at that. I sort of think that the fact that Protobuf might not have all of these features might be a good thing, because in conversion and interpreting, you have unlimited power, right? You have full C++, and everyone knows how to write C++ already, so you don't need to learn like a new format to write these effectively. So it might be a feature, but I'm definitely going to be taking a look at that. Yeah.
Yeah, because at the third point you said converting, and we also had to do pseudocode phase to interpret that pseudocode that results like with the functions and the headers, and you have to parse that one more time, basically adding another overhead. That kind of can already be done with AFL Smart, and we were really proud with the results we had with it. And yeah, I was curious if you're even considering using it in the future instead of writing your own custom fuzzers.
Well, I mean, I don't really consider it that different from writing something with libProtobuf Mutator. I mean, and that's primarily what we use for writing these things. Like I said, I think all the examples that I presented in this talk were written using libProtobuf Mutator.
Okay, cool. Thanks.
Thanks for the question.